Okay, we discussed the chapter 5, the discrete random variable. So we made the histogram and we took the mean and the standard deviation by another 6 steps. And we had an example, it's named the binomial distribution last time. So we used the probability function to get the probability. Yep, it's here, this one. Good, right? And today, additionally, we are going to take the mean and the standard deviation. But before the new topic, I want to review one of the homeworks. So when you go to the Pearson's MyLab assignments, already I posted, not yet, I don't know. Anyway, number 12, because I think I posted number 13, but let me check later. The number 12 tonight is due tonight. In number 1, I ask you the big parentheses. Remember the C function from your calculator? It returned the number of combinations, the number of cases. And number 2, it asks us a probability by formula, or even you can take the probability from the binomial table. Now, it is the binomial table. You know, for the binomial distribution, always we need the 2 things. What is the n, the number of independent trials, and what is the probability of success? So on the table, yeah, it is the binomial distribution table. In the first column, there is the n, how many independent trials. It's up there, the probability of success. And now here is the number of x, the random variable. So it depends on the 3 values. Even we pick a probability from the table. The probability will be exactly same as the probability by the probability formula in part A. So please compare them. Either way, we can take the same probabilities. And the question number 3, yeah, it's the same thing. It's another n, another probability. Yeah, you can take the probability by the formula, or you can take the probability from the table. And now here, yeah, is the regular one is number 4, 5, and 6 and 7. So I want to try one of them. So any question, please pick one among the 4, 5, 6, 7. What is your lucky number? It's up to the last one is a 7. Yes, 7, 6, 5, 4. Which one do you want to together? 7. Okay, good. The last one. Let me copy and paste. Paint. Right. Yep, here. Okay, it is the number 7 in the homework. Please read it. Let me prepare some more space to solve it. Good. Okay, what? You know, always for the binomial distribution, it's at least binomial. We need the is how many n and what is the probability of success. So can you get the number of trials? How many? 64. And can you see the probability of success? 4%, yes. You know the defective, it is not success. But as I told you, we have only 2 outcomes. The target interest, that is a success. There's a number of defectives, it's 4%, it's 0.04. And the question is, what is the probability? It's x. In this case, the random variable x is the number of defectives. It's equal to, it's exactly 3. And now we can apply the probability formula for the binomial distribution. N, 64, Now x equals 3, and the probability of defectives was is 0.043 times 1 minus 0.04 and 64 minus 3. So now let me take part by part. So 64 using the C function. 64 and take the C and 3. I have 41,664 combinations. And the second term, the probability of success, defectives, 0.04 power 3. It is 0.40000064. It is a very small probability. And now the last one is 1 minus 0.04 will be 0.96. And the power is 64 subtract 3 is 61. The power will be 61. I have a 0.082898. So now let me take the multiplications. It's a 41,664 times. The second one is the 0.000064. And the last one was 0.082898. The overall, the multiplication will be 0.221048. Here, the choice B. Good, right? Can you remember? How did we get the probability in the binomial distribution? So always we are using the formula. And the formula has the 3 terms. Yep, individually, you take the 3 terms and finally take the multiplication. But remember, we are looking for a probability. What was the property number 1 for the probabilities in chapter 4? Any probabilities must be between 0 and 1, less than 1. As many students before who got bigger than 1 probability. Wrong. Never, ever bigger than 1. Must be between 0 and 1. Remember, right? Yeah. So it is the probability at 3. Let me show you another probabilities in Excel. You know the Excel is another good software, right? So let me put this n equal to 64. And the probability, the defectives was 0.04. Now, the possible values for x always 0. No defectives. Always in the binomial is from 0. And discrete, countable, random variable is 1, 2, 3, up to 64. See, now we are tossing a coin 10 times. We can have only up to 10 heads out of 10 tossed. We cannot get 11. It's the same thing. We had 64 items. The maximum possible number of defectives is up to 64. It's always in the binomial distribution is up to the n. And was the independent trials, right? And now in Excel, you know the Excel is a good software for statistics, right? So I can go to the function, and let me select the statistical as a categories, and now I need the probability from the binomial distribution. So let me down a little bit. And here is the function is named the binom.dist, stand for the binomial distribution. So let me take the function is a binom.dist, and the number of success from 0. I'm sorry. again. Go to the function, statistical, select the binom dist. The number of successes is 0, and the number of trials is 64, and the probability of success was 0.4. And Excel, the function binom dist returns the two kinds of the probabilities. One is the cumulative probability, but now I need the individual probabilities. So let me say the capital letter first. False, because I need the individual, it's not cumulative probability. Then now I just keep the probability in D1. So let me put the $sign and let me copy down up to 64. Okay, it's good. And I just got the probability at x equals 3. Uh-oh, something wrong. Just a second.
You did 0.4 instead of 0.04.
Oh, thank you. 0.04. Then fixed it. Can you see the probability at 3? Was it 0.22 something? Right? Yeah, why not? You know, Excel is another. It's a good calculator. Yeah, it's using the function. Can you see the function name is up there? It's equal to the binom.dist. Then we can take the probabilities. And when I take the sum up, all possible probabilities from x equals 0 to x equals 64, how much do you expect the sum of all possible probabilities? 1, yes, 100%. Okay, because rectangle, the Venn diagram, rectangle was the sample space. What was the sample space? All possible outcomes. Yeah, same idea. Some of the all possible probabilities for any kind of random variable, it must be 100%. Now, let me show you the histogram. Let me take the probabilities and insert the bar graph for the histogram. Yep. Let me make this smaller. Yep. Here is the histogram. It is not from 1 to 65, but let me select. It must be from 0 to 64, the n, up to the n. So let me modify the histogram. Yep, here it is. It is the binomial distribution. Even I put some space between the bars, but somewhere, we can delete the spaces between the bars. So that is the histogram for the binomial distribution. Just a second. I suggest to you today, we are going to discuss the mean and the standard deviation. You know, the binomial distribution is one of the example of the discrete random variable. So later, by 6 steps, let me take the standard deviation. But first, think about the mean from the histogram. Mean was the measure of the center. How do you think? Where is the center? You know, at 2.2567, there is the most probability, right? So do you think the value 2 is the mean? It is the center. Why not?
Because there's more data on the right.
Because C is the more probability. When I compare the two probabilities at 1 and 3, right? When I compare the probability at 1 and 3, the 3 has the more probability. Absolutely, it is not symmetrical. So here is the more probability. When I compare is 1 and 4, here's a more. And here is a little bit, it's a little bit, even though it's getting smaller and smaller and smaller and smaller, but there is some more probabilities on the right-hand side. So do you expect the mean will be bigger than 2 or smaller than 2? Smaller than 2?
No, bigger than 2.
Bigger than 2. Let me check. Let me check. Let me take the probability. I'm sorry. Let me take the mean using the formula. What was the formula? Take the multiplications and then sum up, right? So even though we have many values, it doesn't matter. Take the multiplication and copy down. And again, let me take the sum. Mean will be a little bit bigger than 2. Right hand side, 2.56. Does it make sense, right? Additionally, 5 more steps. Let me take the standard deviation, right? So, step number 2, what? In step 2, I have to take the difference minus the mean. It will be negative 2.56. Why? 0 minus 2.56 will be negative 2.56. Let me keep the line and copy down up to 64. What will be next step 3? We have to take the square. Copy down up to 64. What will be step 4? Multiply its probability, then copy down. What is a step 5? Now we take the sum. Step 6, finally, we take the square root of it. Then the standard deviation will be how much? 1.56767. 6 steps in the binomial distribution. It's good, right? So by the formula, 2.56 was the mean. 6 steps for the discrete random variable, the standard deviation will be 1.56767. You can do it because the binomial distribution is one of the discrete random variable. Classically, we can take the two things, is the mean and the standard deviation. But can you try just take the multiplication n times p? How many n was? How many n was? 64. What was the probability of defectives? P 0.04. Try it. Yeah, simply just take the multiplication. 64 en, number of independent trials, times the p, probability of success, 4%, 0.04. How much would be? Did you get 2.56? Huh, interesting. What we did before, we take multiplications each, then take the sum. But now, simply, we just take the multiplication n times the probability will be same as the mean. Yes, it is true. See, we had a shortcut. Simply, we take the probability for each using the formula. Here's another one. It's very simple to take the mean. We don't have to take the multiplications each and then sum up. We don't have to. Just multiply n times the probability. It will be same as the mean. Now, how about this? N times p times 1 minus the p. I mean, 64 times is 0.04. Already we did. Additionally, times 1 minus 0.04. I mean, it's a 2.56 times is 0.96, please. Additionally, multiply 1 minus the probability 0.04. Try it. Anybody who got something? 2.4576. Where is the value? In step 5, there is the value. 2.4576. For this, it was the variance. We discussed the range, variance, standard deviation in chapter 3. The value in step 5 in chapter 3, it was the variance. Additionally, take the square root of it. Now, it is the standard deviation. We don't have to apply 6 steps. It's very easy. Take the n times probability times 1 minus the probability. And don't forget, take the square root. Not by 6 steps. Simply, we can take the standard deviation. But remember, it is only true in the binomial distribution. So we have any example, any condition, satisfy the assumptions for the binomial distribution. What? Only 2 outcomes, independent n trials. In each trial, we had the same probability. Then we can apply the binomial distribution. Only in the binomial distribution, simply we can take the probability using the probability function and mean standard deviation. Very simple. It is very simple. Okay? So let me finish the example, the binomial distribution. Yep, here is the mean, the mu, and the sigma, standard deviation. Only in the binomial distribution. Okay, is it good? Okay, today let me introduce you is another discrete random variable named the Poisson distribution. The Poisson distribution is a discrete type, right? So we can define the Poisson distribution as the number of something. So let me ask you, let's see, how many text messages you receive in a day?
I don't know.
How on average? About
20.
20, how many? Text messages. 25 or more, friend? How many? Or, yeah, give me the number. At least 17? Okay. I think it was 17. How many? In a day. Text messages. 30? 20? 25? 30? 20? 20? As for me, I have 2 or 3 text messages from my wife. I asked on the way home, open the cartoon box, check one by one. But think about on my birthday. Who knows? I can get more than 30 from my family members and friends. Yeah. And so how many did you say?
20.
20? Is it always 20?
Um,
Sometimes it's more than 20, right? So who knows? On your birthday, it could be more than 100, right? Is there anybody who can say this one is my limit? We can't, right? Let me ask you another question. How many do you expect a car accident in a week in Fort Smith? Yes.
Do I expect?
Yeah, you expect, yes. In a week in Fort Smith.
Unfortunately, like myself, being in an accident.
Yes. Statistics.
Probably like every time I go out, right?
So, give me the number. Yes.
7 times a week.
7 times a week?
Yeah.
Oh, you mean the seven accidents in a day? Then I asked you in a week, then 7 times 7 will be 49. It's about 50? About 50 in a week? How many do you expect?
75.
A lot, yes, but give me the number. How many accidents in a week? Car accidents.
75.
Oh, 75. Oh, sorry. 75? Oh, wow. How many do you expect a car accident in Fayetteville? Rogers is up there. Oh, shit. On the highway 49? Yeah?
20.
Oh, come on. He expected 49.
I don't know how he.
I'm so sorry. Oh, my God. Yeah, it's an estimation, you know. You know, what I want to say, there is no limit. Think about the snow day. Christmas Eve. White Christmas. Night. Friday. We can expect there's more car accidents, right? Fayetteville, there is more traffic. Absolutely. We can expect there's more than 49, right? It's a snow day. Oh my God, don't go there. Yeah, White Christmas, please stay home. Yeah, it's a crazy outside, right? See, when we discuss the binomial distribution, when we toss a coin 10 times, we can have is only up to 10 heads. From 0, no head, up to 10, right? Before, we had 64 items. How many possible maximum number of defectives? Up to 64. It's no more than 65 because we had only 64. In the binomial distribution, there is a limit. But sometimes we cannot determine the limit. So look at this one. In a hospital, emergency room, between 6 and 7, we can have a random variable. It's the number of patients is arriving, the ER. You know, here's a lambda. Here's another, the Greek letter is a lambda. It's a 6.9. It is on average. In the past history record, they count on average, they had 6.9 patients is arriving at ER. When? Between 6 and 7. You know, when I ask you the number of text messages, and I told you in a day. It's car accidents in a week in Fort Smith. You know, when we think about the Poisson distribution, we have to suggest a very specific time zone and the regional place. Because we can expect there's more car accident at the Fayetteville, and you know the snow day, Friday night, yeah, we can expect there's more patients arriving at the ER. It's between 6 and 7. But it didn't say the days, but it's only saying that between 6 and 7, and the average is 6.9. So it is another example of the discrete random variable as a number of something, but sometimes we cannot determine the limit. Then we cannot use the binomial distribution. We need another one. The another one is the Poisson is a distribution. So the Poisson distribution is another the discrete random variable. And now we have 3 terms. Yeah, we can take one by one. We can take one by one and merge them together to get the probability again. So now, at least we need the lambda, the average, to get the probability. Then now here, we need the probability exactly x equal 4. Simply I apply the probability function is up there. So I just copy E. Then power is the negative lambda. Lambda was a 6.9. The average the number of patients is arriving ER, time the lambda 6.9, and now it's x equal 4, and the 4 factorial. Let me take one by one. E to the negative 6.9. Do you know what is the E? Do you know pi? Not eating pie, but in math, pi. How much is the pi? 3.14. Only 3.14? Yeah, 14156712. I don't know. I cannot remember. Endless, right? The E is almost the same constant like pi, but E, it is a 2 point something. I cannot remember. It's a 2 point some 2 point blah 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 blah. It's forever. But don't worry about that. We have the E on your calculator. So now here I have a TI-84. So now here, can you see that? If you have a TI-84, yeah, the blue one, there is a E with the power X. So if you have a TI-84, please click second first and take the key ln. And how much was the lambda? Lambda was, the average was 6.9 in the example. So don't forget, it's a negative 6.9. Close it and enter. Oops, sorry. Let me try again. Second, E, yeah, negative 6.9. It will be 0.001007. Anybody who cannot find the E on your calculator? The E. Oh. Interesting. Oh. Let me tell you later. You must have the E somewhere. Yeah. Anybody up to you guys? E? The second, yeah, here. There's a second L and T. Anybody else? I'm sorry, I will let you know later. In your case, you have an E here, right?
Yeah, second.
No, so in your case, you plug the negative, sorry, you plug the 6.9 in negative and take this, the reverse way. Yeah. So the E part is 0.001. So let me take the E part, 0.001. And can you take the second one? The 6.9 with the power 4. So here is the 6.9 power 4. I have a 2266.71. And you know the last one is a factorial, right? Before we use the C function for the binomial distribution. Do you remember where was the C? Please go to the place where you got the C function. The next one, there is the factorial, that one. So please plug 4. Please plug 4 first, and then go to the place where you got the C function. Then the next one, there is the factorial. Please let me know if you cannot find the factorial. In your case, you got the C function here. So 4 first, and go for probability. And the second one was the C function, but the next one is the factorial. I have a 24. It's a 4 and math and probability. The C function was the number 3, but now number 4 is a factorial. 24. Everybody got 24? You have a factorial, right? Yes. Yeah. Okay, so divided by 24. So what is the probability finally? Remember, even though the numerator is a 2266, but finally it must be less than 1 because it is a probability. So it's 0.001 times 2266.71 over 24. I have a 0.0944. That is the probability we are going to get exactly 4 patients at ER, arriving at ER between 6 and 7. It's good? Right? Let me try the next one. At most, we need a probability at most 2 patients. Just a second. What does that mean? At most 2. At most 2. 2 or less. But in the binomial distribution, in the Poisson distribution, always we began from 0. 2 or less. 0, 1, or 2. It means, what is the probability? No patient, 1 patient, or 2 patients. So we can apply the probability function 3 times at x equals 0, at x equals 1, additionally at x equals 2. And then we take the sum. Do you have an idea? At least 2. At least 2 means 2 or less. But it's not only the Poisson distribution, but also the discrete random variable binomial distribution started is from 0. Discrete, countable, 0, 1, and 2. So we have to apply the probability function 3 times and sum up. So let me try this one is later. Then now, let me apply E, negative 6.9 times 6.9. Still, we keep the lambda, the average. Now x equals 0 and 0 factorial. 6.9 times 6.9 power 1 and 1 factorial. And E, 6.9 times 6.9 square and 2 factorial. Already we got how much was the E part. So every single probability we plug is 0.001, 0.001, 0.001. The E part, the same, fixed. And now, how much will be the 6.9 with the power 0? You know, before we knew is that any value with the power 0 was 1. Can you take the 0 factorial? It is not 0. Thank you. Try it. 0 factorial will be 1. And how much will be the 6.9 with the power 1? With the power 1, It was itself 6.9. And anybody who tried 1 factorial, it will be 1 again. Very interesting. The 0 factorial is 1, and 1 factorial is a 1 again. And the last one, 6.9 square. 6.9 square will be, say again? 47.61. And how much will be the 2 factorial? 2. Huh, interesting. 0 factorial is a 1, 1 factorial, 1, 2 factorial is a 2. How much do you expect a 3 factorial? Try it. 6. Yeah, another one. Yeah. So every single time, please take the factorial. Yeah, 3 factorial will be 6. It's not 3. Anyway, so it will be 0.001. 6.9 times 0.001 will be 0.0069, and 47.61 times 0.001 divided by 2. The last one will be 0.0238. And simply we just take the sum. That will be the probability at most 2 or less patients arriving young. It's between 6 and 7. So far, good, right? Okay. Any question? So now we have another as a random variable. It's named the Poisson distribution. And now here is a quiz number 13.
No.
For the Poisson distribution, we need the average. We need the lambda. Now here the lambda is the average, the number of earthquake in 22 years. How many times earthquake in 22 years on average? Just once. Once in 22 years every day. So here's the you don't have to do this one. So we need the probability. It's a no earthquake in 22 years, and here's the at least one. So now in part A, we need the probability x equal 0, no earthquake. Then the e to the negative lambda 1, and the lambda 1 times 0 and 0 factorial. So piece by piece, please take them all and take the multiplication. And we are going to discuss the part B is a little bit later. So please try to take the probability. Yeah. Did I give you? Anybody else? I didn't give you back, please. Back. Everybody, got yours? You got it? I can say the 0 power will be 1, and already we knew the 0 factorial is a 1, right? So it will be same as e to the negative 1. So how much was the e to the negative 1? Anybody? 0.3679. Okay, good. Now then, at least. Let me ask you. Can you drink alcohol? Can you drink alcohol? Legal? I'm sorry. Can you?
Not legally yet.
Legally, yeah? Why? How?
Like not legally what?
I mean, you said yes or no?
No.
Legally, no.
Yeah.
Right? Why not?
I'm not 21.
It's not 21, right? Can you see the statement? If you want to drink, you must be at least 21. What does it mean? 21 or younger, older, right? So please remember, at least means 1 or more. It is the probability 1 or more. At least. You know, at most was the other one, or less. But now, at least 21 is 1 or more. Okay? So, absolutely, it must be 1, 2, 3, 4. Just a second. The Poisson distribution is going to what? Did we have any limit? Unlimited, right? It's up to infinity. Uh-oh. Any idea? We are going to take the sum infinity probabilities from 1 to infinity. Just a second. Let me ask you. If I take the sum from 0, 1, 2 to infinity, how much do you expect? How much was the sum of all possible probabilities? 1. I told you. Even though infinity, but the probability is getting down and down and down, even we take the sum of the infinite probabilities from 0 up to infinity, always 100%. But now here, we need the probability from 1 to infinity. Any idea? Yes. Say again loudly.
We subtract the.
We subtract minus the probability x is only equal to 0 minus the probability is x is equal to 0. See? We take the sum all possible probabilities except x equals 0. That will be same as the probability from 1 to infinity. What was the name of the rule? Complementation rule. Do you remember the complementation rule? So the probability from 0 to infinity, it will be same as 1 minus the probability only at 0. How much was the probability only at 0? In part A, already we got 0.3679. So how much will be the subtraction from 1?
0.3.
Thank you. That will be the probability at least 1 or more. So even though we need the infinite sum probability from 1, but apply the complementation rule, we can take the sum of the infinite probabilities in the Poisson distribution. Let me look for STI let me move. I have no idea. Thank you. Have a good day. I will post the new homework. Thank you. You have another thing with this, right?
Yeah, we have a game tomorrow at Oklahoma, and then we have a game this week at Butler Home. So we'll be here.
Oh, okay, good, good. What about the Wednesday?
This one? Yeah, we're here.
Yeah.